Let's do some examples of some surface integrals of the kind of gnarly, flux variety. Okay. All right. Let's see here. I have one right here. Okay. So here's an example. Find the flux of F equal to X, Y, 3 outward, okay, through the paraboloid Z equal to X squared plus Y squared. Okay. Okay, so I want the outward, and let's do this for Z less than or equal to 4. Okay, so in other words, let me just kind of draw a picture of the surface that we're dealing with here. Okay, so look, we have this paraboloid like this, but I'm not letting this thing just go on forever. I'm cutting this thing off at some point. Where am I cutting it off? At Z equal to 4, that's right. Okay, so this is our surface right here, and it includes, by the way, it includes the top and the sides of this thing. Okay, so it includes the top and the sides of this thing. So here's the top right here. Okay, so this is our surface S. Okay. So, okay, so that's interesting. So what do you think that we would have to do to compute this thing? If I want the outward flux through this paraboloid, and if I actually, let's not worry about, hang on a second. I want to delete that, and I'm just going to say, oops. I'm just going to say that this thing is, I just want the surface itself. Okay, let's say no top. No top in this particular case. So I want the outward flux through this paraboloid in this particular case. Okay. Okay, so I want the flux of F through S. Oops. Through S. And by the way, this is outward flux. Okay. So what does that mean about our normals? Stare at that picture for a minute. Just stare at it for a minute. Do I want downward normals or upward normals? Think about it for a second. If I want to go out through this thing, that will imply something about the perpendicular vectors that we use. Will the perpendicular vectors have negative z coordinates or positive z coordinates? Negative z coordinates. Okay. So outward means that we're going to have negative z coordinate on n. So that means I want the downward oriented normal. Yes? Okay, the downward oriented normal. Okay. I think that we're in a position to be able to compute this thing. We want the double integral over S, F dotted within ds. Okay, and that's going to be the double integral over S. Okay. Let's see here. It's going to be F dotted with the gradient of G, where what's G? G is going to be, since I want the downward oriented normal, it's going to be, x squared plus y squared minus z, yes? Okay. And this is going to be dA, okay? All right. So, what do we do? Well, look, to parametrize this thing is sort of stupid. We know how this thing is parametrized, don't you see? Like we could parametrize this thing this way. We can just use X and Y as they are. Okay, so I have the X coordinate, I have the Y coordinate. What is the Z coordinate going to be if I'm going to be on this surface itself? What's the Z coordinate going to be?
X squared plus y squared.
Yeah, it's given by just X squared plus Y squared, for crying out loud. Yeah. Okay. Yeah, okay. So this thing is equal to the double integral. Okay. Now we're going to have to kind of think about some stuff down here, but we'll come back and do that in just a second. But let's kind of just write down what the vector field is. The vector field was X comma Y comma 3. Okay. The gradient of G, okay, that's 2X comma 2Y comma -1. Now you might be saying to yourself, well, for crying out loud, which do you want, Hammett? Do you want to do the partial derivatives of the parametrize thing, or do you want to do this thing with, like, you know, this 4-dimensional surface computing the gradient? Well, it turns out in this case we actually have our choice. Okay, like for instance, if I would have gone up here, and by the way, this is dA. If I would have gone up here and computed like Rx, okay, what's Rx equal to? What's that? What's Rx? What's the X derivative of our parametrized surface?
102x.
102x, exactly right. Okay, and what is the Y derivative of this thing? Well, 0, 1, 2y. Yeah, see what I'm saying here? Okay, and if I do Rx crossed with Ry, okay, you know, maybe I'll just come up here and do this. Okay, so if I go up here and I compute Rx crossed with Ry, okay, what do I get? Well, I get -2x, comma, okay, so let's think about it for a second. It would be, cross out the first entries, it would be 0 times 2y minus 1 times 2x, yes? So -2x, and then I'm telling you it would be -2y, comma 1. But then you would have to say to yourself, don't you see that's almost exactly the same thing that we got doing it the other way? The one difference is this has been negated in relationship to what's sitting inside of this. But we would know to fix that, wouldn't we? Because we would have to think, if I want to go out, then the Z coordinates need to be what? Negative, yeah? So I would have to fix that anyways when I went through this, okay? So I have this thing right here. And I think we're in a position to deal with stuff. We will figure out what these limits of integration are in just a minute. But let's go ahead and compute the dot product of these things. Okay, x times 2x is 2x squared. Okay, y times 2y is 2y squared. Okay, and then I have -3, and then this is dA. Okay, but what's going on with this? Okay, what are the limits of integration going to be? Okay, well, I kind of need to figure that out, don't I? Okay, I kind of need to figure that out. I go up here to this surface. I need to look at what the shadow of this thing is down in the XY plane, since I parametrize stuff in terms of X and Y. What do you think this is going to look like? What do you think the shadow of this surface is going to look like down in the XY plane? If you had to muster a guess right now, what do you think?
A circle.
Yeah. Of course. Of course. Okay. Okay, so let's do that, right? So it's got to be something like this. Okay. Now, what is that circle? Well, this intersection, right where we cut this thing off, was at height 4, yes? And of course, this surface was given by z equal to x squared plus y squared, correct? Yeah. Okay, so z equal to 4 and z equal to x squared plus y squared sort of tells me that this curve that represents the shadow of this surface down in the xy plane is given by what? What would that be? X squared plus y squared what? Equals 4, right? So this thing is a circle of radius 2, if you will, yeah? That's what the shadow of this thing kind of looks like down here. Okay. Got it? So that said, I think that we have a nice option in terms of how we might proceed. I mean, seriously, did you see that? That was a disk, correct? So what manner of integration do you think might behoove us to pursue? What do you think? Look, polar, especially, look at the stinking integrand right here. I have 2x squared plus 2y squared. What is that? You know, x squared plus y squared is what? R squared. Okay. So like this is going to be the integral. It's going to be 2r squared minus 3. Okay. And then I'm converting to polar coordinates. So this is going to be r dr d theta. Yeah. And if I want to get the whole surface, I have to go throughout that whole shadow down on the xy plane, which means theta itself goes from where to where? 0 to 2 pi. And as that happens, what does r go between? 0 and 2. 0 and 2. And yet again, right? I mean, we've played this game enough times at this point that we should be able to predict the sorts of things that that we tend to do. There are no thetas. There are no thetas in the innermost part of the integral. Yeah. Therefore, what am I going to do immediately? What am I going to do immediately?
Perform the outer integral.
Yeah, right. So it's just going to be 2 pi, and it's going to be the integral from 0 to 2. Let's go ahead and distribute this r through right here. So it's going to be 2r cubed minus 3r dr. Okay. What do we have? 2 pi. Let's see here. It's going to be 2/4, which is 1/2 r to the 4th, minus 3/2 r squared. And this is evaluated from 0 to 2. Of course, 0 is of no consequence to us. What really matters is 2, don't you see? Yeah. So we're going to get 2 pi. Okay. And 2 to the 4th is 16 divided by 2 is 8. Minus 4 divided by 2 is 2 times 3 is 6. I get 4 pi. I get 4 pi as the total amount of outward flux. All of this was outward flux, don't you see? Okay, no matter where we were in this particular case, our normal vector was always kind of pointing outward in this case. And we made it so that our normal vector was always pointing outward, which means that it had a negative z coordinate in this particular case. Okay. And so we just computed the total amount of outward flux through this surface if we have the outward oriented normal. Okay, 4 pi. Any questions on that? Yeah.
So there's kind of two ways to do it, right? Like parametrizing it or just finding the gradient of G.
That's exactly right. Yeah.
So then you just pick whichever one.
Yeah, whichever one. Sometimes you can do either one. Sometimes, right? You just kind of have to be sort of, sort of flexible. Don't be loose and fancy free, but flexible, right? Because sometimes you will have a parametrization, but and you just use it. Sometimes you will have kind of like the surface equation. You can just straight use it the way that we just did. So sometimes you'll have both options available to you, and you have to think about whether you want the outward flux or the inward flux or the upward flux or the downward flux, right? All of those things are just things that you're going to have to kind of think through when you set up your normal. Does that make sense? So up here, the one danger we could have run into is if we would have just parametrized the thing, initially when we compute the cross product, we end up with the upward oriented normal, don't you see? If we would have used that instead, we would have gotten not the outward flux, but the inward flux. We would have been computing the inward flux through that particular surface, yes? And guess what that would have been? It would have just been the opposite. Seriously, it just negates the thing, for crying out loud, right? It would just be negative 4 pi, yeah? So you just have to be, you kind of have to be on high alert as it pertains to that. Now, what do you think? Okay, at first I kind of said, let's go ahead and put a top on this, but since this was the first example we ever did, I didn't want to do that right away. What do you think we would have done if I would have indeed put a top on this surface as well? Like there would have been an actual top right there, and I still wanted the outward flux. What do you think we would have had to do? What do you think? What would you do if you had two curves where one curve was doing one thing and then you had another curve doing something else? What would you have done? Do two integrals? Yeah. If I put a top on that surface, you would split it up into two surfaces, don't you see? One of which would have only the paraboloid in play, the other of which would have been a flat top, yeah? That surface would have just been a flat top and you would have computed the upward oriented normal everywhere, which is really, really easy to compute. It would have just been like 0, 0, 1 or something like that, yeah? So it would have been super easy to deal with, okay? But let's keep it simple for right now, for sure, okay? So you can split up these surface integrals into various pieces if you need to, okay? All right, any other questions on that? Any other questions? Okay. All right, so let's do another example because we need to do some more examples. Okay. Find the flux of F equal to negative y x to z outward through, okay, so outward, that is a key word, outward through the sphere x squared plus y squared plus z squared equals 25. Okay. Now, what is that sphere? Yeah.
The sphere centered at 0, 0, 0 with a radius of 25.
Not a radius of 25, but a radius of what?
5.
Yeah, that's right. Okay. Okay, so this is a radius of 5. Okay, so you know, this thing goes out 5 units, 5 units. Okay, and 5 units in this direction. Okay, my proportions are a little bit off here, but you know what I mean. Yes. Now here is kind of something that's tricky about this one. Do you already see? You already see what might be a little bit tricky here? I asked for the outward flux, which means that at every point on this surface, yeah, at every point on this surface, I want the normal vector to point outward, yes? I want the normal vector to point outward. The reason you do this sort of thing, by the way, is oftentimes you'll have some kind of source in the middle of a surface of some kind, and everything will be kind of coming out from that source itself. And you want like the outward flux through the surface, okay? Okay, so notice that up here, my normal vectors look like this, okay? But down here, my normal vectors look like this. See what I'm saying? Yeah. Okay, so down there, my normal vectors look like that. Up there, my normal vector looks like that, which means sometimes I want the upward oriented normal, and sometimes I want the downward oriented normal. Okay, which makes it seem like I might, at first, it makes it seem like I might have to actually split this thing up into two pieces, namely the upper hemisphere and the lower hemisphere. You see what I'm saying? But is there a way? So look, I always want the outward oriented normal, outward oriented normal. Is there a way to do both of those things at once? Is there a way that we can get a normal vector that will always work? What do you think?
Something with spherical coordinates.
Well, not that, let's not be that complicated. But that's, I mean, that's a good idea. I mean, what did we do when we had a surface E equal to little g of xy? We wanted to realize that the surface is just like the level surface of some four-dimensional graph, yes? Couldn't we do something like that here? Couldn't we maybe put like capital G of XYZ equal to, okay, what do you think I should do here? Just to realize this sphere as the level surface of some four-dimensional graph, how should I represent capital G of XYZ? What do you think? I'll give you a hint. X squared plus Y squared plus Z squared. What? Minus 25. Yeah. Okay. Huh. And what happens? So you know that this guy right here is a level surface of G, right? Capital G. Therefore, the gradient of this thing will be perpendicular to that level surface, which is a good thing for us, yes? Okay. So let's compute the gradient of this thing. The gradient of this thing is what? What's the gradient of this four-dimensional graph? What's that given by? Not a trick question. What's the gradient of this given by?
2x, 2y, 2z.
2x, 2y, 2z. And notice, hey, this is kind of nice. Look at this. This guy right here, the third coordinate, this guy is positive if z is greater than 0. And what else is true? It's negative if z is less than 0. Right? So what can we say with certitude about this guy? This is always outward oriented. See what I mean? That thing is always outward oriented in this particular case. Okay, so what do you think we're going to do?
Integral of our flux that we found, our force, and cross it with the integral. Sorry.
Or dot it?
Yeah.
Yeah. Yeah. Okay. So let's do that, right? So we want the double integral over this sphere, which we'll call S. Okay. So this is our sphere right here, S. Okay. We want the double integral over this thing, and it's going to be F dotted with N ds. Okay. F dotted with N ds. Now, the thing is, we kind of do need to parametrize this thing. So N, so what I was saying here was that N we could take here to just be the gradient of G divided by the length of the gradient of G. Okay. Okay. So, let's see here. Let's see here. So, but you know that this length of the gradient of G thing is going to cancel in this particular case. Okay, so let's go like this. So first of all, it's going to be the double integral, okay, of what? Double integral over S. What was F again? Let's kind of look up here, negative X or negative Y, comma X, comma 2Z. Okay, and I'm going to dot that with what?
Gradient of G.
Yeah, 2x, comma 2y, comma 2z. Okay, and this is dA. But then the question becomes, excuse me, like, what do I do with x, y, and z? Yeah? Because after all, we need to be on the surface S itself, yes? So I need to somehow parametrize X, Y, and Z so that we actually are on the surface of this sphere, yes? We've kind of taken care of everything else. We've made sure we have the outward oriented normal, okay? We're ready to take the dot product here, but I need to parametrize this thing, okay? I need to parametrize. Need to parametrize this thing, okay? All right, so Daniel, now what do I do? Okay, you might try to do some kind of spherical coordinates, right? In fact, look, we're on a sphere, so what could be more appropriate than using the spherical coordinates? Yes? Okay. Now, do you remember X was equal to, now what was it? X was equal to, what were the formulas for the spherical coordinates? X equal to, Y equal to, Z equal to.
X equal to rho cosine theta sine phi.
Rho sine phi, yeah. Cosine of theta, because after all, what we discovered was this guy right here, rho sine phi was really just R, right? Y was equal to rho sine phi sine of theta. And what was Z? What was Z? Rho cosine of phi. That's exactly right. Okay, now, if I stare at this thing long enough, I realize that rho is always the same thing. What's rho? What's rho all the time here? Yeah, rho is always 5. So this is going to just be 5 sine phi cosine of theta. Okay, y is going to be 5 sine phi sine of theta. And z, of course, is just going to be 5 cosine of phi. Okay, and what are the, okay, so that's what x, y, and z are equal to in our parametrization for this thing. Yeah. Okay. So what about phi and theta, though? What's up with those guys? I want to get the whole sphere. What about phi and theta? Yeah, Jason.
Phi just goes from 0 to pi.
Right, phi just goes from 0 to pi. Remember, phi can never be, right, phi can never go beyond pi, right? I mean, phi going from 0 to pi gets me everything from the top to the bottom, yes? It's the angle from the positive z-axis, okay? So down here, we go 0 equal to or less than phi equal to or less than pi. And then what was the other one?
0.
Yeah, 0 equal to or less than theta, right? Theta is basically the angle from the positive x-axis all the way around, right? If I kind of looked at the projection of this point on a segment from the origin down into the xy plane. Okay, so it's 0 equal to or less than theta equal to or less than 2 pi. Now, oh boy, right? Think about it. I have x, y's, and z's up here. This looked fairly simple, didn't it? Negative x or negative y, comma x, comma 2z. And I have this other thing sitting right here. Don't you see? Yeah. I mean, this looked fairly simple, didn't it? This looked fairly simple up here. But what's about to happen? It's going to look, yeah, Maria.
First two of the dot product are going to cancel. You just end up with the-
Right. So you're going to end up with like 2z, or you're going to end up with 4z squared or something like that. Yes. Right. So the first two, so like it's going to be negative 2x or 2x times negative y, and then x times 2y. You're going to get some nice cancellation there. You're going to end up with like 4z squared or something. Yeah. So it looks to me like you're going to end up with a fairly nice thing to integrate. Okay. When you think about it for a second. Okay. But can you guys see that once you kind of plug in the parametrization, even if you have stuff that's fairly nice, like for f and for the normal vector itself, like you can end up with some fairly nightmarish integrands fairly quickly, yes? Even for something as simple as a sphere, okay? We're not gonna be able to finish this right now. We'll finish it when we come back on Friday. But let me just say the following. The last two lectures on Friday and on Monday, all we're going to do is try to find easier ways to actually compute these surface integrals. Yes? We're going to have a way to do it called the divergence theorem that will actually relieve us from even having to find a parametrization at all. But these things can get fairly gnarly fairly quickly if you always have to do it the way that we're doing right now. But we'll finish this one on Friday, and we will come back and talk about some stuff.
Divergence.